Hello, Aluko Favor, can you hear me?
Yes, sir. Yes, sir.
Okay. We'll soon start, eh?
Okay, sir.
Victor, can you hear me? Victor, can you hear me?
Victor can hear you.
Okay. David,
Sir.
Can you hear me? Oluremi, can you hear me?
Yes, sir. Yes, I can hear you, sir.
What can you see on the screen?
Right now, a slide for a hypothetical reaction in which B. I can see one of the slides, Jam.
Okay. Thank you.
All right, sir.
Ologun, can you hear me? Ologun.
And the man unmuted me now.
David, can you Ologun, can you hear me?
Yes, sir.
Okay. David,
What's that? Yeah.
I don't understand. Starting at the time is when somebody asks me,
Hey, asked us to go on 1 month warning strike, official release. My check.
what are these?
On some status.
Other physics and to start maybe by tomorrow. I already read what the man was about. That's what they said tomorrow. They said it's most likely to start tomorrow.
They let us do matric first. So at least you take picture before you start packing back.
You should just cancel the matric. What makes sense? You don't do matric and start going home. Pack your bag and start going home.
I can't wait for I can't do that queue again. That queue of getting matric gown.
You take a matric gown home now. Where will you return it? Return it and not do matric again now.
Because they will let you return it. That's when I bought Nike. And you pay 500 naira for it. You think they'll let you return it? They'll take it to Mada. Don't dialogue with them now. It's between them and government.
This guy looks happy about it.
I'm neutral. Like as
happy than sad.
let me just because one thing is certain, if we go on strike, I know now that I've already resumed, it's back-to-back reading I'll start doing. So either ways, I'm not going to be affected much like that. And if it's not go on strike, same thing, I'm still going to read. So there's no thing. There's no that stop.
If you want to buy that Star 121 for
Star
special
121 for good bundles.
No, like 131. But I think I can get 121. Let me see. For special offer. My monthly is not working. If someone does not too much, you remove the person. Depending on your plans. My sister has been doing that thing for 1 year. It has not. Every day she needs 200 naira. So depends on the plan.
Which plan? What's the code?
Star 121. Star
I want one. They removed it from you.
I don't know. This thing. That's when you have balls, these blocks, everything.
That's scary.
I just didn't come and announce the strike.
I'm not here. I didn't get this part.
Baby, can you hear me? Baby, can you hear me?
Give me money and I
Can
want
you see the
to
slide?
guy.
What can you see? Look at that.
Okay. Keep quiet. I don't want to mute you. Keep quiet so that we can start. Already, I have done the uploading of the lectures. Good morning, everyone.
Good morning,
Good morning, everyone.
Good morning, sir.
Okay. Thank you. Now let us go. You can remember, I taught you this on Thursday, and I've already done the uploading. If you go to the platform, LMS platform, you will see this particular lecture I taught you on Thursday. And I was using their table to work out the order with respect to each of the reactants. And I did say that these are the reactants. This is another one. This is another one. So they affect the formation of bromine in. Stop talking. I don't want to mute everybody so that I can hear some of you. Stop talking.
They follow due process. Click on the link for Monday classes. It might have closed by now.
I want to determine the order with respect to each of the reactors. So I have a table, and I've taught you, and I said experiment 4. I did not provide data which you can use.
300.
So I did not provide data which you can use to work out the order with respect to.
Please, sir, can you mute us?
Yes, I'll mute you people.
See, man, just wow.
Please forward that link for me. All this Monday. That link now, I don't know.
Okay. So that is below. This is the rate of reaction is proportional to the bromate, the bromide, and the acidic medium, the hydrogen ion concentration. So I need to perform a simple experiment to determine the order with respect to the bromate, to the bromide, and the hydrogen ion concentration so that I can write a complete rate law. And I did say that experiment 4, I did not provide values for this, and also concentration for this, and also the relative rate of formation of bromine. So you cannot work out the order with respect to, I think, to bromine. You cannot work out the order. If you look at this, all these are constant. They are all constant. What I need to do at this point, I will enter a concentration. If you look at this point, this is 0.06, 0.06. When I at this point, I'll put 0.06 so that everything here will be constant. The same thing, I will alter this. I will put a concentration value there, and I'll put a concentration value there. And here I will put relative rate so that I can find the order with respect to bromide. Last week you did bromate and you did the hydrogen ion concentration. I think that's all. If I want to give you a test, what I need to do is to enter values into experiment 4. And I will enter all the concentration and enter the relative rate, and then you can find the value of M. Already you find L and you find N. So what is left to calculate M? I did not give you those values. Do not guess. You can't do it now until I give you values. So don't try to do it. If you try to do it, you can enter some values that can help you. But those are not the values we obtain experimentally. I'm only just using experimental values to do these calculations for you. That's just a recap of what I taught you last week. So let's make progress today. Let me get it. Okay. Okay. So when a reaction is made up of multi-steps, it is very important to find the order with respect to each of the reactants. But reactions, I told you, they are made up of elementary steps or processes. And sometimes you can predict the rate law from elementary process. And at that point, the stoichiometric factor of a reactant can coincide with the order of a reaction. So if I give you a problem and say, write the rate law, and I make it very clear that it's an elementary process. If you say the word elementary process, the stoichiometric factor is the same thing as the order with respect to that reactant. If you do not see the phrase elementary reaction, elementary process, elementary step, then you need a table. You need a table like this to find out the order with respect to that particular reactant. This is just an example how I calculated the value of N. Okay, you can, when you do the downloading, you can find out how I was able to get N is equal to 2. Okay, so as I said, the exponent in the rate law appear to be unrelated to the coefficient in the overall balanced chemical equation. If I do not say it's an elementary process, you cannot use the stoichiometric factor to stand for the order of the reactant. Why? It is because reactions are made up of so many steps. And then you need to perform experiment to find out the effect of the reactant on the rate of formation of the product. But as I said earlier, if I say the process is elementary, and then you don't need to go to the table to work it out. You just pick the stoichiometric factor as the order with respect to that particular reactant. That's what I mean. Sometimes, however, the coefficient which you refer to as the stoichiometric factors can coincide with the order of the reactant. It's just a coincidence. Essentially, to find out the order with respect to each of the reactants, you need to perform an experiment. Therefore, the balanced chemical equation, the balanced reaction, the mole factor, the stoichiometric factor, or the molar coefficient do not represent the order, except it is specifically pointed out that it's an elementary process. Okay, look at that. So this morning, let me just give you some quizzes. That is quiz number 2. Look at what you see on the screen. If you have a 1 mole, this means A is undefined reaction. A plus 2B is equal to D. Okay, look at the number of moles of B is 2. The number of moles of A is 1. 1A plus 2B, and that will give you D. So the rate of formation of D, look at D is the product in the above reaction, is found experimentally. So I did the experiment here. If I ask you to write the rate law, you don't have to say A. The order with respect to A is 1. The order with respect to B is 1. No, unless I'm saying that equation 1 is an elementary process. Now it's not an elementary process. So see how you can work out the order of A and the order of B. The rate of formation of D in the above reaction is found experimentally to be dependent of the concentration of B. And that means B does not affect. It means B is a spectator. B will not affect the rate law. Okay? But what happened? And it increased 4 times, quadruple. It increased 4 times when the concentration of A is doubled. So write the rate law. Just as I taught you, if I double the concentration and the rate remains constant, it is 0 order. If I double the concentration and the rate is also double, it means it's first order with respect to that reactant. If I double the concentration and the rate increased 4 times, that is quadruple, it means it's second order. In other words, you can find out what is the order of A. I said when it is concentration of A is double, the rate of the reaction increased 4 times. So what is order with respect to A? Is 2. What is the order with respect to B? Is 0. Because it's saying that the reaction is found experimentally to be independent of the concentration of B. But when the concentration of A is increased 4 times, what happened? When the concentration of A is double, rather, the rate increased 4 times. Therefore, with respect to A, the order is 2. Okay. So what is the answer to that? You can write the rate law. Look at equation 2. For the general rate law, this is the rate law that I've been able to establish for a particular reaction. Look at that. The order with respect to A, this is another question, has no relationship with the first one. The order with respect to A is 1. There is 1 here. I told you if it is 0, we will put it. If it is 1, we do not put it. If it is 2, we will put it. If it is fraction, we put it. If it is 3, we put it. But if you see it like this, look at this place of A. A is raised to power 1. So you don't need to put 1 there. Once you do not see something like 0, 2, 3, 4, it means you have 1 at that particular point. Okay. What is the order with respect to B? The order with respect to B is 2. What is the overall order? 1 plus 2. 1 plus 2. The overall order is 1. This is 1 here plus 2. And that the overall order is 3. Then it's asking you, what will happen to the rate of the reaction if the concentration of A is triple? The concentration of A is triple, that is 3A. Look at 3A here. If you change it from A, 1A to 3A, what will happen to the rate of reaction? The rate of reaction, as you can see, the first one, this is how you do it, rate 1 is equal to K, okay? Then when you have A, you put 1 there, 1A. When you have B, you put 1 there, 1B. 1 raised to power 2 is 1. And then the second one that will help you to know it is rate. The second one. And I'm saying the K is constant and the A is now 3A. 3A, but the order is 1, 3 raised to power 1. And B will also be constant. It's only A that you change to 3. Look at that. K times 1 times 1, that's 1K. That's what you call like 1,000 in your money. What about the second one? What did I do? What will happen if the reaction, if the concentration of A is triple? I have now tripled the concentration of A. Look at it, tripled. What will happen to the rate too? It's going to be 3K. 3K is greater than 1K. And that is why the answer is, can you guess? The answer is going to be C. the answer is going to be C. And that is the rate will be tripled. So that is how to answer simple questions like that. Okay, now let's go on. Another question again. Another question again. Methanol can be produced by the following reaction. Carbon monoxide plus hydrogen, and that will give you ethanol. How is the rate of disappearance of hydrogen gas related to the rate of appearance of methanol? You know, I told you, if you want to write for the rate of disappearance of carbon monoxide, it's a reactant, you say minus D into CO over dt, and that will be equal to minus 1 over 2. Remember, look at that. The rate of 1 over 2, you know what I mean by 1 over 2, into the hydrogen over dt. And that will also be equal to plus D into methanol over dt. So I'm asking you, how is the rate of disappearance of hydrogen gas related to the rate of appearance of methanol? So you write like this, rate, capital R if you like, and that will be equal to, you write for the disappearance of hydrogen, and that is 1 over 2. You know why you are dividing it by 2, into D, into the concentration of hydrogen. This is a defined reaction, hydrogen, okay? And then you divide it by what? By dt, okay? And that will be equal. How is it related to the rate of appearance of methanol? Then you put plus. If you put minus here, then you will miss it. D into the concentration of methanol. Look at that. It's here. You put it inside here, and then you close the bracket over dt. That is the relationship between them. Don't go and be writing carbon monoxide. I did not ask you that. I did not ask you carbon monoxide. Okay, I ask you, how is the rate of disappearance of hydrogen gas related to the rate of formation of methanol? This is what is needed, and that is the answer. Where you have plus D into methanol over dt, if you put minus sign here, then you are going to miss it. Remember the minus sign for hydrogen gas because it is a reactant, and the product, there should be a plus in front of it. That is the answer to this particular question. Okay, I've given you how to answer questions from my first lecture, second lecture, like that. So let's go on and see what we can do today. I think I still have another question to ask you. If you download, you will find the questions there. If you're having problem, please let me know. Look at that. What is it? This one is very simple. What is the overall order for a reaction represented by the rate law? What is the overall order of reaction represented by the rate law? Look at, you see the rate law. Rate is equal to K into hydrogen raised to power 1 and into nitric oxide. And I'm asking you, what is the overall order? Is this 0? No, it's not 0. Hydrogen is raised to power 1 and nitric oxide is raised to power 2. So what is it? Oh, is it 0? No, A is wrong. Is it first order? No, B is wrong. Is it second order? No, C is wrong. Is it third order? Yes. 1. This is 1. I told you they don't put it, so assume that it is there. And this is 2. 1 plus 2 is 3. I mean it is third order. So I've given you so many examples from what I have taught you for the past 1 week. And I guess if you see questions like that, you should be able to answer them. So prepare for my test by Thursday. Thursday this week, by God's grace. Thursday, prepare for test. Okay, now let's go on. Today, we're going to discuss, I'm going to talk about molecularity, mechanism, predicted rate law, and units of rate constant. Remember, we have been looking at the rate law, and I said the rate law, rate, R is equal to K into a reactant, and then raised to a power. This is example of a first order reaction. This K, I told you, is the specific rate constant. And then we're going to look at how you can calculate the units of the specific rate constant. Concentration, I told you, of A of a reactant is mole per dmq. So we're going to look at molecularity, and then look at predicted rate law, and then look at the unit of the specific rate constant. Okay. Okay. So what do you do today? They represent so what are you going to do today? That is, you'll be able to calculate the unit of the specific rate constant when you are given the order of a reaction. Is it first order? If I say this is first order, calculate the unit of the specific rate constant, and then you should be able to do that. Is it second order? Is it third order? And then you can calculate the unit of the specific rate constant. Okay, reactions, as I told you, when I taught you about mechanism of a reaction, reactions are made up of steps. And all these steps are referred to as elementary processes or elementary steps. And some of the steps are very fast, and some of them are very slow. The one that the slowest step is the rate determining step. For example, a trivial example is if you are traveling to Lagos, okay, if you run into a holdup, which you call go slow, that is your rate determining step. That is the slowest step. You cannot be faster than your slowest step. If you want to come into the university and you're finding it difficult to pass JAM becomes the slowest step, and that is the rate determining step. You were able to pass your WAEC in a very brilliant way, and then you can pass other exams, but if you're unable to pass JAM, determining step. So some reactions, they also have a slow step, then they have very fast steps. So the slowest step determines the rate of a reaction, and the number of molecules that can take part in that on the reactant side in a rate determining step will determine the molecularity of a particular reaction. Well, I'll give you an example that will help you. Look at that. An overall balanced chemical equation, like hydrogen is reacting with oxygen to give H2O. What you see is the balanced chemical reaction, which is called the stoichiometry of the reaction. Okay, this will not explain to you what are the steps that are involved in giving you this stoichiometric equation. So there are steps that are involved, which you call the elementary steps, and then which form the mechanism of the reaction. So mechanism is already explained, so I'm not going to talk about that. And that is the way the reaction is occurring, and then the summation of the elementary steps that will determine the overall balanced chemical equation. So all that I have here in the next 1 or 2 slides are the things that I have taught you. It's a collection of individual kinetic processes, elementary steps that are involved in transforming. I told you chemistry is this with transformation. It's about transform from one form to another, reactant to product. And all the steps that are involved are what I use in explaining to you what you understand by the molecularity of a reaction. And I did explain to you, look at what you have there, that if you take, I have been using this all along. Dinitrogen pentoxide, look at that. If you heat it at a very high temperature, it can decompose to give you nitrogen 4 oxide and oxygen. And so how did you get this stoichiometric equation? And I did say it's made up of steps. And I gave you about 3 steps to explain how I'm able to get this particular product, the oxygen and the nitrogen 4 oxide. Look at that. So I'm going to use this to explain to you now. The first step is a slow step. Okay, the second step. So you have 3 steps here. 1, 2, and that is 3. Each step is an elementary process. Each step is a process that will lead to the formation of the product. So the first step, look at that. How many molecules are taking part in the first step? How many molecules? 1. So the molecularity of the first step is 1. How many molecules are taking part in the second step? 2. You have nitrogen 4 oxide, nitrogen 6 oxide. Okay. Now what about the last step? How many molecules? 2. So what did I say about molecularity? Reactions are made up of so many steps. Example, the nitrogen pentoxide. And I've been able to establish 3 steps. And each one has a process which you call elementary step. And the number of molecules that are taking part on the reactant side. Look at this. This is the reactant side. Before you get to the arrow, look at that. On your left-hand side, those are the reactants. The number of molecules that are taking part in this elementary step, 1. The molecularity of this step is 1. The number of molecules taking part in this step, 2. The molecularity here is 2. The number of molecules taking part here is 3. The molecularity here, 2. Molecularity here is 2. And as the molecularity, it can be worked out from the elementary steps, elementary process. And that is the number of species or molecules taking part on the reactant side of that elementary step. You don't go to your right-hand side, begin to count from left-hand side to your right-hand side. No, count only the number of molecules on your left-hand side of that particular step. If you do so, and then you will be able to calculate the number. For example, if I want to change expression 3 like this. If I put 3 here, look at equation 3 on your screen. If I ask you to work out the number of molecules taking part, that is the molecularity. Here is 4. Now I have changed it to 4. 1 plus 3. If I come here and I ask you work out the molecularity here is 2. 1, 1. If I come here and I put 2 here, for example, and I ask you to work out the number of molecularity for expression 1, it's now 2. 2. So what do you understand by molecularity? Is a number of species, a number of reactants taking place on the reactant side of an elementary process. Sometimes reactions, as I told you, some steps are very fast, some steps are slow. Okay, so we use molecularity to define, to characterize. We use it to characterize each elementary process. But when you now talk about the overall molecularity of a particular reaction, you can use the molecularity of the slowest step to characterize that particular reaction. That is why I said if you are traveling to Lagos and then you run into a holdup, which is go slow, you cannot be faster. It's not possible. You cannot be faster than that particular holdup. Okay, so that will determine how fast you get to Lagos. Immediately you get out of that holdup, you drive faster. So that holdup now becomes the rate determined step. So the slowest step is the rate limiting step. The slowest step is the rate determining step. And the number of molecules on the reactant side taking part that will lead to the formation of the product in that particular elementary step will give you the molecularity of that reaction. Now I will come back to it later, and I want to teach you something. So try and pick it. If you pick it now, you'll be able to pick it as we go along. If I ask you to write the rate law of this particular reaction, you just use the rate, use the expression for the lowest step. Look at the lowest step, is the first one. If I ask you to write the rate law, this is how you write it, using the slowest step of this reaction. And I'm saying that the first expression is an elementary process. Immediately you hear the phrase elementary process, okay, you just write rate. For this particular reaction, just write rate equal into K. Then you use the lowest step to represent it. N 2, 0, or O rather, O5. Okay, you close it. The order is 1 because the number of molecules taking part in that particular process is 1. And if I say the slowest step is number 2, and I ask you to write the rate of this particular reaction, and this is elementary process, use the second expression to write the rate law. When you go to that, you write the rate, okay, equal into K. Okay, what are the reactants? It's only the reactants you deal with. NO2. What is the rate? How many molecules are there? 1. And then you write for the second one, N 0, O rather. Okay, raised to what power? 1 molecule. And that is how you can immediately you see the phrase or you hear the phrase elementary process. At that point, the most stoichiometric factor of the balanced chemical reaction will automatically coincide with the order of that particular reactant. That is the only time. It's just a mere coincidence, okay? Because we've already qualified the reaction to be elementary process. But when it's not an elementary process, then you need a table, you need concentration, and monitor the effect of the concentration, of the reactant, how they are affecting the formation of the product, so that it can work out. It's easier if you just see the expression elementary process, you pick the stoichiometric factors and use them to represent the order with respect to that particular reactant. So I have taught you that, and you have so many questions like that, very common. Okay. So let's go ahead. Molecularity, the mechanism of a reaction and how to write the rate law. Let me clear the screen for you so that you can follow me very well. Okay. Okay, let's go. Molecularity, you now know. Why are you using talking about the molecularity of a reaction? I did say that reactions are made of so many steps. So what you see on the board or rather on the screen is what I've already explained to you. What is a rate determining step? Reactions are made up of some steps, and the slowest step is the rate determining step. I use your journey to Lagos as a kind of example to help you to understand faster. An elementary process, we use it to characterize the number of molecules of the reactant, okay, reacting at that particular elementary step. We use it to characterize that particular reaction. Remember, when you are picking the molecularity, look at only the reactant on your left-hand side of the equation. So I've explained all this to you. What do you mean by elementary process? Why do I call it elementary process? Why? I give that to you as an assignment. Why am I calling a reaction expression an elementary process? And I told you that is the only point where the stoichiometry of the stoichiometric factor or the number of moles of the reactant will agree or will be equal, or the coefficient of the reactant will be equal to the number of molecules or equal to the number of, or equal to the order of that particular reactant. Okay. Okay. So let's qualify reactions. If you see a reaction in which the number of molecules that are decomposing is just one, you refer to that as unimolecular. An elementary step in which only one reactant of the molecule is participating in that reaction, you call it unimolecular. If it is two molecules, for example, if I have something like this, A is reacting to give B, this particular reaction with respect to A is unimolecular reaction. But if I have something like this, 2B, okay, they collide to give C. Or it can be A plus B reacting to give C. Two molecules are involved. You call it bimolecular. If it is three molecules are involved, you call it thermomolecular. Some people will say trimolecular, but I will prefer to call it thermomolecular that are involved. So if I'm talking about bimolecular reaction, it means if it's an elementary process, obviously you should be able to know that the order with respect to that reactant is 2. And if I say I have an elementary process and it is unimolecular, write out the rate law. You should know that the order with respect to the reactant is 1. So these are some of the things that can also help you. Unimolecular, 1 molecule. Bimolecular, 2 molecules. Thermomolecular, 3 molecules are involved. By the time you go beyond that, it becomes very difficult. It's difficult to get 4 molecules to coincide. To collide at the same time. Okay, let's keep going and see what we can cover today. Okay, screen is clear now. Let's see what happened. Okay, I've explained all this. When you download, you will see the rate of elementary reaction is proportional to the product of the concentration of the reactant that are involved in that step. So when I say a step is an elementary process, you can write the rate law. Rate law, rate expression, rate equation, they are the same. The way I'm using them. Okay, rate is equal to K, RATE, or capital R, or you can write for the rate of decrease to represent that particular reactant will be equal to K into each of the reactants raised to the appropriate power. Okay, so I've explained all this. Take this for example. Consider the reaction. Okay, phosphorus pentachloride. It will decompose to form phosphorus trichloride and chlorine. I can write a mechanism for this. Look at the mechanism. It's just a mechanism that I propose to satisfy my final balanced chemical equation. Slow. The step 2 is also very fast. And you can add up. Add the 2 equations. They are elementary process. Add them up. You see that PSC4 is on the right-hand side, and equation 2, you also have it. So you cancel, you remove it. You remove the left on your left-hand side is this. Okay. And then you add up what again is left to your left, this, and then you add up 2 chlorine atoms that give you a molecule of chlorine. And that is the balanced chemical equation. If I ask you to predict the rate law, for this particular reaction, how do you do it? You use the slowest step to represent the rate of the reaction. Which is the slowest step? Is the first step. And how do you write the rate law? It's an elementary process. the experimentally determined rate law is equal to what? To this. This is the experimentally determined. But as I predict, just tell me what you think it will be theoretically. You use the slowest step to write it. How do you write it? Rate is equal. Sorry, this is missing. Equality sign is missing here. Is equal to K into PCl raised to power 1. Look at that. The slowest step has 1 molecule. And I'm referring to it as elementary step. So you use the slowest step to predict it. The predicted rate law and the experimentally determined rate law should be equal. They should agree. If not, then your mechanism is not very correct. Look at what I determined experimentally. And then I'm asking you, why don't you just predict theoretically? You use the elementary step that is very slow to predict it. Rate is equal to K into C. How many molecules of PCl5? One of them. So it is raised to power 1. This is the rate determined step. So you can predict the rate law from the rate determined step of a chemical reaction. Okay. Okay, now let's keep going and see what we can do. Look, and that is, I have explained this when you download, and then you'll be able to find out what I'm talking about. Let me give you another example. Look at what you have on the lower part of the screen. For example, A will react with C to give D. And I'm going to work out a mechanism for this. How do I do that? How am I going to do it? To work out a mechanism. A will react with C to give D.
Good morning.
Look at that. A is a slow process. A will go to B. It's a slow process. I'm going to work out a mechanism. I said
Morning,
A
sir.
plus C.
Yes, sir.
Yes, sir.
How was the weekend, sir?
Fine, thank you.
Thank God.
Yes, sir.
Good morning, ma.
Yes, sir.
Thanks. All right.
How far with the letter? Have you got it?
A will react to give B, and that is very slow. As soon as B is formed, very quickly, B will react with C to give D. So add up. The overall reaction that I wanted is A plus C to give D. This is the slow step and the fast step are the ways I have used to give account of the reaction. And when I add up all the steps, I will be able to get A plus C, and that will give me D. How did I get that? I just cancel what is on my right-hand side, and that is B, and I cancel this B, and I add up. And that is, so you can use these steps. If I say A will decompose to give B, is a slow steps elementary process, use it to predict the rate of the reaction. All you just need to do is you write rate is equal to K into A raised to power X, where X, how many molecules are here? 1. Then you just change this place to be 1. Raise A to power 1, and that's all. If it is B, that is a slow step. Right now, B is not a slow step. Okay, it's a fast step. So you don't use B to predict the rate of this chemical reaction. I'm just telling you how you can predict the rate of a chemical reaction from the mechanism of a particular reaction. Okay, I will leave this, and let me correct it so that I leave this one for you and see what you can do with it. Look at this. This 2C react with D to give E plus F. And then I'm going to work out a mechanism. 2C, and then we go forward. There's an equilibrium here for the fast reaction. And then look at that. As soon as C2 is formed, C2 will react with D. Look at D, and then it will form E plus F. This is a slow step. And if I ask you, use the rate determined step. The rate determined step is the slowest step. Use the rate determined step to work out the order, the overall order of the reaction. All you need to do is look at that. K rate. Use the rate, that is capital R or small r, whatever, into K. Use the rate determine step C2. Look at that. C2 raised to what power? It's elementary process. It's just only one molecule. And then, and the products are these, you have D raised to how many? The order. The order is also 1 raised to power 1. What is the K? Look at the first equation, the equilibrium reaction. To come forward, you have K1. Look at K1 here. To go back, C2 will go back to C, you have K2. So correct, when you download, put K3 here. So this is K3. And then that means this place is supposed to be K3. So this is the rate law. But you need to work out expression for C2. Look at C2. Work out expression for C2. We don't need C2. It looks like as if it's a side reaction. Very fast. As soon as it's produced, very quickly it will react with D, and that will give you E plus F. So, and I'm proposing this expression as the rate equation. So how do I eliminate C2? I want to remove C2 because C2 is a side reactant. Okay, it came out of the process, and as soon as it is formed, it is consumed. So it doesn't stay for too long. So we're going to remove it from that particular reaction. How do we do it? Look at that. If you are going forward, rate of going forward, what will react to go forward? Look at that. You are going forward. It's elementary process. What is reacting? C. How many molecules? It's elementary process. 2. You raise it to power 2. Okay. Then what about to come back? What will react to come back? What will react to come back? Then we go to write expression for what will react to come back. And that is, we're going to see it in the second slide in a minute. Okay, look at that. To come back, that will be C2 will be reacting to come back to give C. It's an equilibrium reaction, backward reaction. So what happened? Look at Roman 1. If you look at Roman 1, you find out that the two reactions, to go forward K1 and to come back K2, they are equal. So you write expression for C2. We want to remove C2 because C2 came up during the process of the reaction. And then we go to remove it. So we derive expression for C2. And then the expression for C2 involves K1, K2 over C raised to power 2. So what is the rate law? What is the rate law? And I ask you to use the slowest step to predict the rate of the chemical reaction. And that is K3. What are the things are reacting? In expression 3, you have C2 and D. Okay, we want to remove this C2. And we've already derived expression for C2. And what is the expression for C2? This is the expression. You substitute this one in place of C2. Look at this C2 here. When you substitute that, and then what you have is the rate of the chemical reaction. Okay, so this is how you can predict the rate of a chemical reaction from the slowest step of that particular reaction. From the slowest step, you don't need to do experiment to find the order. Immediately they say it's an elementary process, the stoichiometric factor becomes the order of that particular reactant. So read the question very well to find out, is it an elementary process or is it a step that is made up of a reaction that is made up of so many processes? And then you need to use the concentration of each of the reactant to work out the order with respect to that particular reactant. Okay, let's keep going. I think we'll cover more today. Look at that. We want to, then this will take us to another topic, unit of the rate constant. Why am I talking about the unit of the rate constant? Look at a typical rate law. Rate equal into K. If the reactant is just one, just A, that is decomposing, and let's say it's an elementary process, first order. Look at that. That is, what is rate? When you are traveling, very quickly, if you understand, then you'll be able to work out this very fast. If you are traveling, what is your speed? 100 kilometers per hour, okay? That is, in chemistry, you change it to concentration, mole per dm cube per unit time. What is your time? Per second. So your rate becomes mole per dm cube per unit time. K is the specific rate constant, and A is the molar concentration. I've taught you this sign before. A, that means mole per dm cube. I don't need to be repeating that again. Mole per dm cube. And then how do you work out the unit of K? The only thing that you don't know here now is K. Is K out the unit of K. It is only this K you don't know. Look at that. You don't know this K. But your rate is mole per dm cube per second or per minute or per hour. And then your A is mole per dm cube. So how do you work out this? So the units are worked out from the rate, from the order of that particular, the overall order of that particular reaction. If you rearrange this one, you say the unit of K, rate constant, it becomes the unit of the initial rate of the reaction. That is the speed over the overall order, the unit of the initial concentration of the reactant. For example, let me just quickly do one for you so that you can follow. So how do you work out the unit of the specific rate law? Is it first order? Is it second order? Is it third order? What are the units if it is first order? If it is zero order, what are the units? Okay, look at that. From the question that I wrote before, let me just quickly, with the overall order of a reaction is equal to 1. For example, look at that. B, look at what I'm writing. B is undefined reaction, and that will give you C. If I ask you to write for the rate of decrease of B, you say minus. Why did you put a minus sign there? Because B is a reactant. Minus into dB over dt is equal to what? K, and B is the reactant raised to a power. And I've already said it is first order. Look at that. So it is assumed that here you have 1. I told you all along we don't put it, but it's assumed that it is 1. How do you work out the unit of this? Work out this unit for me. How are you going to do it? You start from here. Look at your rate. What is your rate? Rate is mole, okay, per dm cube per what? Let's use second. Per second, okay, per second, equal to K into B. What are the units of B? Mole. Mole per what? Per dm cube. Per dm cube. Look at that. Then you bracket. Look at your left-hand side. Mole per dm cube. Look at your right-hand side. Mole per dm cube. So what is the unit of K for first order? K is equal to what? Per second. That's all. If you use weeks, it will become per week. If you use hours, it becomes per hour. That's how to work out the unit. What if it is second order? Now, let me give you an assignment. Work out the unit of K. If it is a second order, work out the unit of K if it is a second order. Okay, let's look at it that the rate of decomposition of B is established to be second order. Let me put 2 here. 2. What are the units of this specific rate constant? Start working on it and tell me. Some of you can even guess and be able to. That is the. That, what are you going to put here now? Look at that. Look at its raised to power 2. Therefore, what do you put here? It becomes K mole, okay, per dm cube remember, you have 2. It's raised to power 2, so it's twice. So you cancel one, you just cancel this one here, and then you also cancel 1 here. That's the end. You still have time here. Okay, reciprocal of time. Look at this. 1 mole per dm cube is still remaining. So what do you do? How do you get your K? Your K is equal to what? Then you put it here like this. Your K, you know, 1 mole per dm cube is left here. It becomes mole per dm cube. That's what is remaining. So finally, you can carry mole up. It becomes mole per mole. Take it up, raise it up. It becomes per mole. dm cube per dm cube becomes dm. Remove the minus sign. dm cube. And then remember, there's time there. Per what? Per second. Okay. So the question I want to give to you now is this. Work out the units of specific rate constant. Work out the units of specific rate constant if the overall order of the reaction is 3. If the overall order of the reaction is 3. So I'm giving you this. Work out the units of the specific rate constant if the overall order is 3. So this is what I've given to you. I will ask you to submit when I'm ready for you. Work out the specific rate constant units when the overall order of the reaction is 3. Okay, we have been very slow. We still have a lot to cover. I'm the first lecturer. You still have 5 more lecturers coming. So by the grace of God, the next class, I'm going to be very fast. What I've just given to you this morning, I'm going to upload it this morning. And then you can go to the LMM platform and trying to download it. If you do not understand, try and get in touch with us. In chemistry, we entertain your questions at any time you look for us. We'll be able to answer your question. Or you can send it to us. You could go to the chat platform, and then you can let us know what is your challenges. Okay. So this is, if you look at that, what I mean by mole per dm cube is very clear. When you see this bracket below, and then it's the same thing as mole per dm cube. So you can use molarity. The way they taught you in school, it's even easier for you. Use capital M to represent molarity. Look at that. Very quickly, let me just take you through these questions so that you'll be able to follow. Look at the first question. Look at A reacting with 2B to give D. The rate of formation of D in the above is found to be experimentally to be dependent on the concentration. And I think I've done this for you. So I did something like this morning. Look at that. The general rate law. We'll find out. I think I've also done this for you. And I think, okay. So this book where I have prepared these lectures from, you can always see that the university bookshop. or at the university publishing house. So the next thing, this is the next topic we are going to look at, the order of a reaction. We go again into order. From what we'll be talking about, you will see that the order can be 0, it can be 1, it can be 2, it can be 3, it can be 0.5, it can be -1. It depends on the kind of reaction that you are looking at. And then we'll go into what we call the kinetic equation for reactions. As we are getting to that, most of the things I've been saying, maybe you are familiar with them. But by the time we go to kinetic equation, you are likely to meet things that you haven't heard of before. So this is where we are. Let me make it very clear. I will try and upload the order and the kinetic equation so that you can read them before you call me. So I'll try to be faster so that I can cover what I'm doing and allow another lecturer to come in. Ladies and gentlemen, prepare for my test. And that is, I'll give you a test on Thursday, by the grace of God, if you have lectures. So have a great day and God bless.